Okay, welcome everyone. Today, Lev Borisov from Rutgers will tell us about modular curves and moduli space of realizations of nature.
Thank you. I'd like to thank the organizers for inviting me. So this talk is about the joint work with Xavier Rouleau. And it's about a year and a half old, but there's nothing to report beyond that. So maybe I can speculate some, but not much. So I'll start with the background. Suppose I have complex number tau in an upper half plane. In other words, its imaginary part is positive. And then I want to consider the lattice Z plus Z tau. It's a subgroup of C, additive subgroup of C. So something like this, this will be 1 and this will be tau. And I'm looking at the subgroup generated by it. Okay. And I am interested in the following construct, E, which is the quotient of C by this lattice. And as stated, it's just a complex manifold, one-dimensional. But of course, we know every compact Riemann surface is in fact algebraic. And the way you give it an algebraic structure is by looking at the field of meromorphic functions on it. So what are meromorphic functions? This E, well, you can think of them as double periodic meromorphic functions on the whole C. And by double periodic, I mean that they're periodic with the period 1 and tau. A priori, it's not obvious that there is anything like this other than constants, but it's a standard 19th century construction that you can construct one of them called the Weierstrass function, or if you want to distinguish it from a monstrosity, you call it Weierstrass elliptic function. And it's something like this, if I remember it right. Anyway, some specific series that converges absolutely on compacts and gives you this nice meromorphic function, double periodic. And then the field of meromorphic functions on E is generated over C by the Weierstrass function and its derivative. And they satisfy a relation squared equals some cubic polynomial in the Weierstrass function with coefficients that depend on tau. Okay, this is just sort of a reminder. If you haven't seen it, well, it's your loss. It's really great stuff. But let's see. Okay. Now, this Weierstrass function gives a standard embedding of E into projective plane CP2, which will play a role in the whole talk, a big role. So we have the embedding from E to CP2 defined by sending Z mod the lattice to Weierstrass function of Z, its derivative and 1. This is if Z does not belong to the lattice, and it goes to 0, 1, 0 if Z is in the lattice. And because of the periodicity and because of the memory, this is actually an embedding. You have to work a little bit to prove that it's actually an embedding. And the image is given by a smooth cubic curve. A cubic curve in CP2. And in fact, every elliptic, every such curve in CP2 comes from this construction. In CP2 can be constructed, well, I'll just say can be constructed this way. And you have to find an inflection point and so on and so forth. I don't need those details. So what I will need is the following. One interesting feature of this embedding is that if you have Z1, Z2, Z3 in E, let's say distinct, then Z1 plus Z2 plus Z3 being equal 0 in E. So E is the quotient of additive group by a subgroup, so it has a group structure, it's a compact Lie group. So the sum is 0 in E if and only if the images of these points are collinear in CP2. Right. This is standard 19th century stuff, and you use it to define, for example, geometrically the group law on an elliptic curve. So all sorts of fun stuff. If you're curious how this is proved, a line is given by a linear equation in P prime and 1. Generally speaking, it'll have a pole of order 3 at z equals 0, and then there's a standard result that zeros of a double periodic function counted with minus poles counted with multiplicity add up to a lattice point. So if you have and they're also the number of zeros equal the number of poles. So if you have a pole of order 3, then the zeros will add up to 0, and that's how you go from here to there, and the other way is the same, basically. Right. So what does this tell me? Suppose I look at the point 1 over n. 1 over n is a point of order n in E, right? So this is my fundamental parallelogram. This is my 1 over n. So you have a point of order n. So if you have a subgroup generated by this point, so just more precisely, let's take P0, P1 up to Pn minus 1, which are phi of 0, phi of 1 over n, so on, phi of n minus 1 over n. Then they have the following collinearity properties. Pi, Pj pk are collinear if and only if I plus j plus k is 0 mod n. Okay. So this is what Xavier looked at. And he thought, well, why don't we reverse the procedure? Why don't we look at all collections of points in CP2, of n points in CP2, with these collinearity properties, and just study it? I mean, in the terms of matroids, you have this very specific matroid, and you're looking at, I guess, realizations of this matroid as collections of points in CP2. All right. Yeah, so he started this project. And I haven't been thinking about this stuff for about, I don't know, 10, 15 years. But at some point, he reached out to me, and I'll explain why and what. Right. So, right. So, Xavier looked at the realizations of this matroid. And there's some strange stuff happening for small n. So let's say for n greater or equals 10. And what I think by this is you look at collections of this P0 up to Pn minus 1 in, so I guess the whole thing is in CP2 to the n with collinearity conditions and modular PGL 3C. And he just looked at it numerically. I'll explain how. And he was getting, well, curves. More precisely, these were modular curves, x1 of n. This is not at all surprising. If you haven't seen what x1 of n is, think of it exactly as parametrizing elliptic curves with a choice of point of order n on it. So not surprising at all. But in his approach, they were embedded into somehow, I'll explain, it's sort of a little weird, in a certain projective space, possibly, I mean, of degree equal to degree of divisor of weight 1 modular forms. So this one is sort of to be expected, but this one is not at all clear. And so at this point, he reached out to me, and then we worked together, and we were able to show it, and I'll explain how you can actually see it, and it just what's going on. Yes?
Can you explain the sentence? Equal to degree of divisor?
Yeah, so he had a certain way of realizing this. So the space of realization is actually not a compact curve, but he was constructing it in some way, and there was a natural compactification of it in some projective space. And
literally the sentence. I don't.
Oh,
degree of divisor.
Degree equal to degree of divisor of weight 1 modular forms.
What is the divisor of weight 1 modular?
So x1 of n is a certain curve, It has some line bundles. There is a
So you mean that it divides the dimension of the space of weight one modular forms? Is that what you mean?
No. So weight one, no, not the dimension of the weight, no. But if you pick a weight one modular form on elliptic curve and you look at the number of zeros, that's the degree of the divisor.
Got it.
Yeah, so so we worked on it, and in the process we found something that was surprising to me related to those weight one modular forms. And but before I do that, I have to explain how what exactly he was doing.
What's different when n is small?
Oh, well, you have this. So, for example, you have this modular PGLN, right? So you just don't get. So you just get some degenerate cases. I mean, you can compute it; it's no problem. But it's just not going to be x1 of n. The dimension will be different even. So because it's like for example, let's say n equals 2. 2 points, because collinearity like is irrelevant. Even 4, right? I mean, it's just wrong, right? No, you have to have. So no, he computed all the smaller ones. That's not so interesting because it's just numerical. He was actually. It's also possible to find x1 of n for small n by modifying your matroid a little bit. So he did that. But for me, the interesting part is when n is larger. Yeah, so what he did is he got up to maybe n equals 42 numerically. So he had this conjecture that it's x1 of n in a certain embedding, but he didn't know how to prove it. But then he reached out to me, and it wasn't too long afterwards that we were able to do it. But what was he doing? So suppose you have this n greater or equal 10, just for simplicity. And what he said is, okay, we have points P0, P1, P2, P3. And if n is at least 10, these points are not supposed to be collinear, and no 3 of them are collinear, so they're in general position. In general position means you might as well assume that they are this 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, right? And then pk for other k, except for the case n minus 3, for an important reason, will be of the form 1 ak bk. What's special with n minus 3? Or maybe we might as well cyclically order it. So what happens is p minus 3 is the intersection of p1, p2, and p1, p2, and p0, p3. And so p negative 3 just has to be 0, 1, 1. There is no choice. But then nothing else lies on the first line, because first line is P1, P2. We have a realization of this matroid, so all the others must have non-zero first entry. Might as well scale it. Perfect. You have this matrix with these unknowns, AK, BK. So he wrote collinearity condition. Basically, determinant of the minor is 0 as long as they add up to 0 mod n, and they're distinct, right? So here are all those collinearity conditions. Plugged it into, I don't remember, Macaulay or Magma. And then, so this gives you, this puts you inside some affine space, but then you compactify it naturally in a projective space, and that was what he was getting. And he could see for small n that he was getting a smooth curve. X1 of n was a natural guess, so you could see, yeah, I mean, it was all pretty clear. And he could get the degree as well by looking at Hilbert polynomial. I mean, like now this thing is of course not graded, but when you homogenize, so you get some kind of, in C, I don't know, 2n minus 6 or something, or 2 times n minus 5. And then you put it in CP, 2 times n minus 5. And then somehow some of these conditions are linear, so it actually goes down to a smaller projective space. And the compactification was somehow he was getting it inside here. And okay. So this was great, but now we want to see how we actually, like why, how do we know that something like this has to come from an elliptic curve, for example? It's not too bad. Yeah, I have to sort of say that the paper is fairly elementary. We're really not using any heavy machinery.
That 2n minus 5 to
Yeah, where do I get it? So you see just over here, right? Like how many A's and K's are there? Right? There's n. So you see like there are 5 points accounted for. There's n minus 5 afterwards. Yeah.
But then you linearly project?
No, not linear project, but when you write some of those determinants, you're gonna get some linear relations on A's and B's. So technically it sits inside here, but it sits in a projective subspace, linear subspace of it. So he got rid of basically all the linear terms, and then he got that. Yeah.
What is the genus of X1n?
It grows roughly linearly. It depends on some divisors for a prime. I want to say p minus 5 times p minus 7 over 24. So it's something like n squared over 20. No. Yes, maybe. Yes. So quadratic, about n squared over 24, give or take. Yeah. All right. Yeah. So how do you connect it to elliptic curves? And that's his work. Maybe I cleaned it up a little, but that's basically his work. So what you do is you say, okay, you look at p minus 1, same as p n minus 1. So p minus 1 lies in p0, p1, but it does not lie in, so it lies in p0, p1, but so you can see that p minus 1 has to be 1s0. Yeah. So in other words, p0, p1 is the line that the last coordinate is 0. And so the b has to be 0 there. And I'll just denote the a negative 1 by s. Fine. You do p negative 2. You can see that it has to be s over s minus 1, and s cannot be 1. And p minus 3 we already computed. P minus 4, you can compute that the second one has to be 1. And this one, again, introducing another parameter t. We're going to have two parameters at this point, because what we're effectively doing is we're looking at an open subset at M12. So elliptic curve with the choice of point, because the order n you cannot see from here. And then you have, from here you can compute P4, there's also P3, I forgot to write it down. Anyway, P3, P4, P5, you compute in terms of S and T. And then you find that there is a unique up to scaling cubic curve passing through them. This is where you need n greater or equal 10. If you don't, then this is not going to work quite as neatly because you cannot say that things have to, like stuff breaks down, right? You need n sufficiently large not to introduce some additional linear dependencies. And I had too much time on my hands, and so I copied this equation. It's nothing. I mean, it's just an equation, right? So it's a cubic equation. Well, no, I mean, you could do it by hand if you wanted to, but why would you? Of course, we used Mathematica, and it's nothing. It's nothing horrible, and you can prove that it's unique. So somehow there are some minors in there, and you factor them, and based on what's not collinear, you can say that the minor is non-zero. So it has to be this unique one. And so generically for S and T generic is going to be a smooth curve. If S and T are not generic, then you play with it a little bit, and it's annoying, but you can check that you're gonna end up getting a rational nodal curve. So S and T not generic. Oh, you get this. So what happens here is rational nodal curve is also almost a group. If you remove these 2 points, you get C star, and then you look for subgroups of order n in C star, and those have to be that, because you're essentially, and then subgroups of order n on C star, there's the nth root of unity, and I should have copied those. No, those are too ugly. I don't think even copying those would make much sense. Yeah, anyway, and then you take sort of arbitrary, and then so basically you have some solutions which you have control over, and that's fine. And then you argue that if the curve is smooth, then you have to start with a point of order n. And that's it. So at least as a level of sets, you see how you're coming from x1 of n. Now, what does this have to do with weight 1 modular forms? All right. So,
Can you remind us what are the special points in x1 of n that does not correspond to Moduli?
yeah, so basically what happens is you have upper half plane. You have a quotient of it by a certain group. And this was the part that I was talking about where you have a tau here, and then you're looking at lattices generated by Z and tau. But this will be just an open part in the x1 of n, but you have to add a little bit extra, a finite number of points called cusps. So the full x1 of n as a set looks like this. You take H, disjoint union Q, and the special point I infinity, and you take a quotient of that by gamma 1 of n. So it's the set of orbits of this group gamma 1 of n. I'll say what it is at some point. Should I say it now? Might as well say it now. So gamma 1 of n is the subgroup of SL2Z such that A, so this should be congruent to 0, 1, 1 star 0, 1 mod n in SL2Z. And it acts by Möbius transformation.
S and T satisfy some equation here.
Depending on n, yes. So before I introduce n, they're free. And that just corresponds to the fact that I'm just having an elliptic curve with an arbitrary point, right? And its positive and negative multiple will satisfy those collinearity. Once you put a condition that it has order n, they will satisfy a relation, a complicated one, depending on n. I can't write it out explicitly, but we can still work with it. Yes.
How should I think of the boundary points in x1 n as like curves with some?
Well, so it depends how you want to think of them, right? So, they are this. So if you want to, I mean, so some of them clearly just so the I infinity corresponds to just this specific degeneration, and then but. I'm not sure if the correct way of thinking about other cusps, maybe it's not, maybe it's more complicated. Maybe it's like a chain of, a ring of curves. I mean, I'm not sure, I'm sure it's written down somewhere. I've never really tried. But you can think of it saying, okay, every Riemann surface has a unique compactification, right? So you can, and so that's what they are. But yeah, no, I mean, what's a universal sort of nodal curve with the level structure? I don't know for the specific. Yeah. Okay, right. So how do we see what this embedding looks like? Well, here's what you do. So remember, you have your E, which is C mod Z plus Z tau. And you have this phi, which sends E to the CP2. Yeah. And then you have this, you have phi of the origin is 0, 1, 0. And this is my P0. Phi of 1 over n is Weierstrass function at 1 over n, is derivative at 1 over n, and 1. And this is P1, so on. So phi of k over n, Weierstrass function of k over n is derivative at k over n, and 1. But then what you do, you take this endpoints and you put it in the standard form, meaning you take a PGL3 action to make the first 4 points into 1, 0, 0. Right? 0, 1, 0, 0, 0, 1, 1, 1, 1. And then the case point becomes 1 AK BK. There's something special with the n minus 3 point, but whatever. Yeah. And so you can think of this AK and BK now. Yeah, there's a unique way of doing it, right? Every, because these 4 are not collinear, so there is a unique way of doing it. So now you can think of it as follows. You have a map H from H to, right? So you have a map from H to, if you wish, C to the 2n minus 5, or you can just think of sort of AK and BK, there are functions of tau. And the point is we need to compute them. If we compute them, we know how the x1 of n is embedded into this C to the 2 times n minus 5. Yeah. And they are what's called modular functions. For gamma 1 of n, because this map factors through the quotient. And okay, how do you compute them? Well, to do this, we have to understand what this equivalence, what are we allowed to do in this equivalence. So here is what we're allowed to do. We can scale rows independently. And we can also do GL3C on columns. Right, and that's it. So now you think about it and you see that certain ratios of determinants are going to be invariant under those operations. And these ratios would allow us to compute AK and BK in terms of the Weierstrass function. Let's be more specific. So, for example, BK can be written as a determinant. I'm going to make my matrix starts from row 0 because that's the most sensible thing here. So determinant 0, 1, 4, determinant 1, 2, 3, over determinant 1, 2, 4, 1k, sorry, k, 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 determinant 0, 1, 3. Yeah, so when you write this ratio of determinants, if you do a GL3 on columns, they just all get multiplied by the same number. And the number, the indices, the number of indices of each kind upstairs and downstairs are the same, so scaling rows doesn't do anything either. And this particular one on the right gives me BK. And on the left, it gives me some ugly expression, some ugly determinant in Weierstrass functions. Fine. Now we just have to compute it in terms of our sort of coordinates of choice on x1 of n. And kind of, so what's the method, roughly speaking? So roughly speaking, you do something like this. You look at this matrix, P of 1 over n, P prime of 1 over n, 1, P of 2 over n, so on, P of 3 over n, so on. And then you just, instead of k, you take arbitrary k, but even more, you just work with an arbitrary point. And then you compute this, let's call this thing f k, phi k. And then phi k is an elliptic function. I didn't use the word elliptic, double periodic function. With respect to z plus z tau, which has the following properties: simple poles at z equals 2 over n negative 3 over n, simple zeros at z equals 0, z equals negative 1 over n, and also it has this property phi of, well, it's not phi of k, it's phi of z. Phi of 3 over n is 1. When you have these properties, they determine your function uniquely, and then it becomes a fairly simple procedure. if you've worked with elliptic functions a little bit, but you get the answer in terms of log derivative of the theta function at rational point. So I want to introduce my best friend, well, at some point anyway, the theta function, the Jacobi theta function. So it has two nice representations. One of them is as a sum and another as a product. For some reason, I always write it as a product. So it's a function of two variables. Tau is an upper half plane. Z is a complex number. LZ. L tau, sorry. L tau. L tau plus Z. 1 minus e to the 2 pi I. L tau minus Z. So what it is philosophically, it gives you sort of universal section of a line bundle in an elliptic curve. So it is not double periodic, it has certain transformation properties. But all of those Weierstrass function and all others can be written in terms of this theta. And the interesting ones is these things I'll call SA. SA of tau will be partial derivative of Z with at a rational point. So now A here will be 1 through n minus 1, or basically in Z mod n Z without 0. They have a nice expression in terms of they have nice power series expression in terms of e to the pi I tau. So plus minus sum d greater or equal than 0, e to pi I d tau, sum for t dividing t, and 8 theta minus theta and minus 8. So a very particular case of something called Eisenstein series, I think people call them Hecke form. Well, not Hecke, maybe some people call them Hecke. There's not Hecke eigenforms, but there's, I think, anyway, lots of people considered it. These are weight 1 forms, whatever that means for gamma 1 of n. They're not necessarily all, they don't necessarily form a basis of weight 1 forms. Starting from, even for prime, starting from 23, you may have others, but they are sort of the easy ones, pretty accessible. And so you do that, and you get these formulas. That's what I got initially. 2s3 plus s2. So the formulas look a little ugly. The reason they look a little ugly and sort of very non-symmetric is because we broke the symmetry by forcing the first 4 points to go into the standard form, right? Why did we choose the first 4 points? Well, no good reason, but well, maybe some reasons, but it's how it so happened. And so that makes it a little ugly, but that's okay. No. S5 minus 2 S3 plus S1 over SK plus 2 minus SK plus S1 minus S3. And so I got it. I mean, I just got the B part. And it looked very strange. I was looking for an error in my computation because according to Xavier, we should have an embedding with meromorphic forms. The degree is like that. In that case, I would expect the denominators to be the same. Yeah, this is how it would look like if you have an embedding into CPN and then you take an open part, you just divide by one of the variables. And so you just have some kind of linear combination of s's on the top and a specific s in the denominator. Yeah, and then what made me quite excited is that yes, it turns out that yes, you can actually rewrite it in this way. So something I had no idea a priori, but you can actually, there are some identity on S's that were completely unknown to me, and it's possible that nobody has ever looked at them. Maybe some 19th century paper, somebody pointed it out, because it's not that they're hard to prove. I mean, it's probably all of like one page. So now you see how you just have the same denominator, and then you have an embedding basically using this. And this is why you have the weight one modular forms giving you this particular embedding. More precisely, this is a particular case of the following strange to me property of this S. I'm going to write it down just because it's so amusing. So it's a proposition in our paper. So suppose you have ij mod n. So they're non-zero. They're different from each other. Then sk plus j minus I minus sk minus sj plus si times sk plus j minus sk minus I minus sj minus si is independent, is the same for all k not equal to I minus j, 0, I, and negative j mod n. What's interesting about these, from my point of view, you can also show that these have no zeros in the upper half plane. Yeah. So it's not what you would call cusp forms. Cusp forms are the ones which are vanishing at all those extra points cusp, but they could also have some other zeros. This is, so these are, roughly speaking, these are sort of units on the open part of your modular curve. And I'm actually willing to conjecture that the ratios, since there is no, there is no penalty for making wrong conjectures these days, right? So the ratios of these generate units of this open part of modular curve. For n, I don't know, large enough, or maybe prime if I'm being shy.
But is it known that the open part embeds into L vectors? It's not to be.
I mean, it's a good question. Well, now I think it follows probably. From this, it would follow. But I don't know. I don't know if it's, I'm not sure if it's too hard. What is known, and that's sort of very interesting also, is that it's a standard result of Grinfield and Manin that on the modular curve, the differences between cusps is always of finite order. And somehow, I wonder, I mean, it's something, some numerical computation, I'm gonna have some kind of undergrad or a master student look at it, just to see if the relations coming from this identity, how do they differ from what's already known about the so-called cuspidal group, the subgroup of the Picard group of X1 event generated by the cusps? Yeah, so to me, those were completely unexpected. I did not think that there would be rank 4 relations on the S's. But let me just tell you maybe so in the remaining few minutes. Okay, so I want to say, since I think people here may be interested in arrangements, I will say something that you can ask what happens to this configuration of points at various cusps. So not all cusps, so cusps are the stuff you have to add to get that curve, the whole curve. So at some cusps like I infinity, you just get true realizations of a matroid, nothing interesting. But then at certain cusps, you get what's called Borovsky, I'm not sure I'm pronouncing correctly, arrangement. So in this case, you look something like n equals to m, and the cusp corresponds to a mod m, where GCD of am is 1. So it's the image of this. And what you have there, you have a conic and the line, and you have, I think, two like endpoints on the conic, endpoints on the line in a very specific position. And then in some other case, you get this thing called Cheva arrangement. And there you're on 3 lines, and you have basically some roots of unities on those lines. So they sort of naturally appear. Xavier was somehow excited about it. He actually saw it before he contacted me. I don't know much about matroids. I don't know if it's interesting or not, but maybe it is. You don't get anything much beyond that. So beyond that, it looks some sort of variations on Cheva, but then some points just collapse to a single point. So you don't really get anything beyond these two, but it's interesting that you do get them. Yeah. Now, why do I care about those SAs? So if you look at the span of products of SAs, so n is fixed. I look at the span of products of SASBs. So now these are weight 2 modular forms. I never define them. So if you, yeah, but for people who know what they are. So if you take the cuspidal part of it, whatever, something like this. This is also a span of Hecke eigenforms of analytic rank 0. So in principle, if you could control this S's, like the products in some way, you might get some bounds. I'm not gonna go into details. It's expected, so this is for X1 of n. It's expected that this is almost everything, but so the whole thing grows roughly by Sn squared. The expectation is that the defect grows at most linear. There's no way to prove it at the moment. Even saying that the limit of the dimension of this to the whole space is 1 would be very, very interesting. There's also something, a funny statement that if you take Wronskians, so now this is derivative with respect to tau. So this is span over all A and B. Now, this is also the same as a span of also Hecke eigenform of with L function at the center of the critical string be not equal 0. So now this is weight 4. These are weight 2. So they just have some strange number theoretic properties, which I have, which are traditionally just addressed through analytic methods like circle method and whatnot, and which I know nothing about. But I'm hoping that just some algebraic methods would give you some bounds. It seems, I mean, so let's put it this way. When I gave a talk at Princeton 15 or so years ago, Sarnak just laughed. And when I said, okay, you can maybe do something with it. He thinks it's just too hard. There's something called Goldfield's conjecture, and then it's just, but I don't know. I mean, I did not think that these essays would have those rank 4 relations. So maybe there is something there that one might be able to get. Right. Okay, and I'll stop here. Yes.
So is there an interpretation of Hecke operators in terms of the matrix?
Hecke operators in terms of matroids, I don't know. I mean, so the way this works is Hecke operators more or less act by looking at certain like linear combination of indices here, right? So you look at the sum of matrices of determinant, say D instead of determinant 1, and then you look at like how they act on those. So I don't know. The matroid seems to be too simple to really tell you much of anything. Yeah. I mean, for example, you can also do the same thing, but get instead of this, you can maybe look at you can just do M11, like don't do order n, just because you just had to take the first few and you already got yourself this S and T as the parameters. This is M12. You can even do M12, M13. You know, some of them are no longer rational. How do matroids have anything to do with it? I don't know. Like I don't know. Like to me, the matroid part is sort of the hook that maybe Xavier was interested in, but actually using matroid theory to get something here, maybe. But I'm sort of doubtful. Oh, okay, maybe there is something because there's a question. So you can look at the ring generated by S's, and there's also a related thing called C. But finding syzygists of that might be something that maybe matroids will give you some ideas of what the syzygists might look like, but I don't know. Also, for these guys, you can write exactly what the order of vanishing of them at the cusps are. And it's actually not obvious how you directly prove without all the elliptic functions that those orders add up to the correct degree. But no, but I still have my doubts that matroids would actually be useful. Yeah.
So did you say that if I take like 11 points and look at, sort of.
Yeah.
You get so if you take the closure in the natural space, do you get M112 bar?
No, not M. No. So to do M112, you need to do more points. So you have to look basically instead of just a little segment inside Z, you have to take like Z to the 12, Z to the 11 or something, and you take a little ball inside of that, whatever, 11 to the 11 points or whatever, and then that matroid should give you M111 bar.
Yeah. So like an open subset, but
Yes.
you're gonna get like an open subset of M1.
Yeah, it would be an open subset. Yeah. Not a particularly important open subset, but yes, absolutely.
But then if I take the closure in some natural space, do you think I will get
Well,
11 bar?
compactifications are never really unique, so I don't expect you would get specifically that. But there are some properties of M1 and bar that do depend on the choice of compactification. For example, the Hodge number H0, whatever, n, it's 0 at first, and then it becomes non-zero, right? So that does not depend on the choice compactification. Can you see it from the matrix? I sort of doubt, but who knows?
So the conclusion is that x1n is isomorphic to this particular closure of the realization space.
Yes, particular closure. You can actually specifically say what the realization space is. It's the inside part and the very specific cusps. We know which cusps.
So
Mhm.
the closure of the target being smooth, is that like part of the proof or is it?
No. Well, it's not obvious. We have to prove it. Yeah.
Computationally or?
No, you can do. I mean, it's arbitrary n, right? So how would you prove that? No, but you can look sort of infinitesimally, right? Like what? Yeah. I mean, the point is, once you compute, where are my formulas, right? Well, actually, once you compute that they're given in this way, it's known that that the embedding given by S's is scheme theoretical and embedding, because they basically generate everything in high enough degree in your ring of modular forms. Then it's just a matter of showing that all of these that all of these numerators they linearly span the entire space of S's, and for n larger or equal than 10, it's like a few sentences.
This might be related to you choosing the first 4 points.
Yes, of course. Yeah. If you didn't choose first 4 points, it would be something else other than 6, 3, 2, 1. If you pick different points, you would look different, but it would still be of the same degree.
So I never understood this point about realization spaces. So people want the realization space to be a scheme over Z. And they also want like a geometric points over it corresponds to like point configuration modulo PGL. But I don't know how to take the quotient by something like PGL for scheme over Z. So I've seen people doing like something like this. So maybe fix first 4 points in general position and then the rest write down the equation and you get the scheme over Z.
Yeah, I don't know that this is necessarily. Yeah, I mean, you absolutely could and even put it there. I mean, I don't particularly care because I don't get, but he did definitely. So you can ask what you do, for example, modular prime. But yeah, no, I agree. It's not. I think here you're probably okay because over Z though, over Q I'm okay. Like 4 points over Q can be put in standard form. Over Z I don't quite know. It seems natural, but I don't know.
Well, I was just asking whether is there like some fancy algebraic geometry where one's allowed to take the quotient of a scheme over Z by like a group scheme over Z or something like that?
I would imagine, but I don't know. I mean, I would not be the right person to ask, but in principle, well, yeah, so what happens if you just do something stupid and take ring of invariants? That's wrong, right? But if you just do the sort of the JT style, right? But like if you take an appropriate open, no, I don't know. I don't know. It seems like it's probably makes sense certainly in this case. But I do wonder if you get the same thing if you pick different 4 points to go to both. I don't know that it's necessary.
So I think the current implementation of realization space.
You take 4 points.
Yeah. So input just takes any one basis and then outputs bunch of equations with integer coefficients.
Right. But is it obvious?
Yeah, it's not obvious that different choice
different
will output the isomorphic scheme over etc. So
yeah, I see.
But here the situation you're questioning by PGL, whereas there you're questioning by a torus, which is reductive in positive characteristic. Kind of a better situation.
But still not okay.
Yeah, I'm still not sure. Yeah. I don't know. I don't think about spec Z much, so I can't really tell you.
So before this, how did people write down equations for x1 and with integer coefficients?
Oh, I think the usual approach would be, yeah, I think maybe they would, so you know how there is this J invariant? So certainly for x0 event, which is a related thing, what you could do, so you have this J invariant of tau, and you can write, and you can look at J invariant of tau and J invariant of n tau. And there's a polynomial relation on them called modular polynomial, which you can compute. It gets ugly and ugly and ugly as it gets larger. Beyond that, I think like going back to maybe Deligne, you could just construct it as a stat, or you could just construct it as a modular space of elliptic curve with one marked point, but your concept of elliptic curve with one marked point is sort of abstract. It allows for it allows you to work over spec Z. So I think that would be the original construction, but as a practical computation, they would do this. Yeah, so I don't know. I haven't tried to see like if what we do mod spec Z would correspond to that abstract construction. That would be painful. Yes.
I didn't understand where your equation S and T came from. I'm just.
Which one? S and T?
You had a beautiful equation.
Oh, yeah, no. Yeah. I mean, yeah, so no, it's just what they came from is you just, so you look at the sort of small points, and for example, p negative 1, if I remember correctly, was something like 1 S0. And I think p negative 4, if I remember correctly, was 1 C1 for whatever reason. And then the rest could be computed in terms of S and T. Yeah, maybe I got them slightly wrong, but basically you look at the sort of 10 points or 9 points close to the origin, and you use, and you can compute some of those coordinates using collinearity, and the ones you cannot compute, you declare to be parameters, and this is S and T.
Okay.
How many points were used?
So it's kind of funny. So you can use as many as you want, you know. But what happens is if you pick a certain 9 points, I think from -3 up to 5, then there's a unique one passing through it, which also happens to pass through p negative 4. But if you go from -4 to +4, then it's not unique. So you have to go up to +5, and below you can go up to -3. Yeah, I mean, the number is just because you have 10 cubics, right? So you have to have 9 points to have a unique, to expect to have a unique curve through it.
Okay, let's think once more.